Hello, everyone, and welcome to the decision-making Michelangelo session for those of you who are following along. My name is Peter Kvam, and today I'm going to be talking about a very specific constraint on actually a wide variety of decision-making models, particularly from the perspective of continuous decision-making models. So what I'm going to talk about today is kind of driven by the recent development of continuous response models, right? So when we want to move beyond modeling decisions between 2 to 3 or 4 options, we want to predict decisions among things like color wheel or different spatial orientations or spatial locations, things like prices or magnitude judgments. We need sort of a different class of models. And there's a lot of really exciting work that's been done in these areas in the past couple of years, including work on the circular diffusion model, the spatially continuous diffusion model, and something I worked on a little bit myself, what I call basically a large class of models, basically just called geometric models. And there's a couple reasons to kind of want to use these types of models. And part of that is that they drive interesting new research questions, right? One of the reasons to use them, though, is actually that working from a general kind of model, right? So a model that works for any number of response options, and then building a specific binary choice model or multi-alternative choice model is usually easier than trying to take a binary choice model and figure out how to map that onto a continuous span of response alternatives. Although in some cases that's how these models were developed in the first place. And the second reason to be interested in these models is that actually the representation of evidence in these models is particularly interesting because they represent the information about the stimulus is distinct from the representation of support for each of the options that we might choose, right? And so what happens is as we accumulate information from the stimulus, we represent that separately from the support that we have for available options. And so when those available options change, in cases like things like phantom decoy effects, then we don't lose all that information that we've gathered. This is going to be particularly important when it comes to the sort of effects that I'm going to talk about today. So applying them to discrete choice, I'm going to talk about 4 specific models that I kind of think span the range of ways that we can apply continuous models to discrete choice. The first one is the circular diffusion model. And this one is pretty well fleshed out, which makes it really easy to think about. And the way that this model works is that if we're thinking about a choice between 3 different colors, for instance, right? So maybe we're thinking about a blue, a pink, or a yellow response. We have some stimulus that we're gathering information from. And that stimulus is providing us some color information. And that pushes us towards some colors and away from other colors, right? And as we look at the stimulus for a while, we gather some color-based information. And then once we get enough information, right, we hit the edge of a circle, the circular response boundary. And once we hit that circular response boundary, that's when we stop and we make a choice. And the response that we actually make is based on where on that circle you hit the response boundary. Okay, the second type of model that we look at is actually in many ways very similar, except that there's a separate response boundary for each response alternative. And this is important in different applications of these models that I won't cover today. But basically, the idea is the same, is that you have some representation of the stimulus information that you're gathering that kind of carves a trajectory through this space. And then once you hit a response boundary, either the yellow response, the pink response, or the blue response, you generate a response in favor of that option. And the final one I'm going to talk about actually kind of has 2 versions, and there's 2 different ways to kind of interpret this model. And one of the ways you could kind of instantiate this model is to say that, well, we're actually accumulating information across a wide variety of different color responses we could give, right? So maybe this is like a light blue, a greenish, a kind of yellowish green, a greenish yellow, and it kind of move through the colors over here, but we only have a small set of actual colors that we can respond, right? We just have our blue, our yellow, and our pink here. And so while we're accumulating support across all the different color responses we could give, what happens at the end is we hit the threshold in this case, and we sort that threshold into yellow responses, blue responses, and pink responses, right? So this is what I think of as sort of a post-accumulation sorting. If you contrast that against a different instantiation of the spatially continuous diffusion model, which we think of as more kind of lines up with the RT-Con kind of approach, where before we actually accumulate information, we divide the stimulus information that we're getting into pieces of stimulus information that support a blue response, pieces of stimulus information that support a yellow response, and pieces of stimulus information that support a pink response. And then after we sorted those, we sort them into support for yellow, support for pink, and support for blue. Right? So this is kind of a post or pre-accumulation sorting. And that's really how I'm actually going to divide up these models, is that the first three that I talked about have what we call post-accumulation sorting, right? So you have a representation of the stimulus, and then once you hit some sort of threshold, then you sort the stimulus information into different responses. Let's contrast that against what we call pre-accumulation sorting, which is as soon as you get information from the stimulus, you push that into different bins, right? Accumulator for yellow, accumulator for blue, or an accumulator for pink, right? And this is the sort of approach that traditional diffusion and accumulator models take, right? As soon as you get that information, you say that supports A or that supports B, and you represent that as a balance or as sort of different bins of information. And this is really the comparison that I'm going to be doing today, is contrasting the two theories and sort of testing them against one another. The way I'm going to do that is using an orientation task, right? So this is actually a pretty simple task, is that there's the stimulus on screen. I'll show you the stimulus in a second. You sort of click the left or right mouse button to make that stimulus appear. And then as soon as you're ready to decide whether the orientation of the stimulus is closer to orange or closer to blue, you click the left or right mouse button to indicate orange or blue respectively, and then we record the response time and the response. So pretty typical binary choice response time task. This is what the stimulus actually looks like. Hopefully this shows up okay on the actual videos. Basically there's this stimulus in the middle of the screen, this kind of jittering set of Gabor patches. And there's an orange response, right? This corresponds to one orientation. There's a blue response, right? It corresponds to a different orientation, right? And our task is basically to figure out what the mean of the stimulus orientation is closest to. Okay, so that's basically the basic condition. That's what we call the no switch condition, where you just have the same set of response options the whole time. We contrast that against what we call a switch condition, where the set of response option actually changes across the course of a trial. Right, so we start off with the same stimulus, same response options at the beginning of a trial, but in the switch conditions, one or both of those options is actually going to change partway through. Right, so that looks something more like this. Right, so the stimulus is going here, and about 200 or 400 milliseconds into the trial, one of them changes. Right, so that orange option is changing from its original position to its second position. Okay, the actual experiment details: there's 14 participants. Each person takes about 500 trials. This is about an hour-long task. We have a within subject manipulation, so everybody sees both the switch trials and the non-switch trials. We also tell our participants at the beginning of a trial whether it's going to be a switch trial or non-switch trial. So they're not just waiting in non-switch trials. They know that they can make their response as soon as they're ready to make it. And what we're going to do is we're going to compare patterns of response times and accuracy between the switch and the non-switch condition. Right. So we're going to compare. Did you actually speed up in some conditions or slow down in some conditions when we changed the set of response options that was available? And we're actually ran 10 types of different switches. We're only going to look at 7. We're missing a couple types that participants had particular trouble with, which was changing discriminability, where both those options would switch out or in towards the stimulus, as well as switches where the correct option changes. We're not going to look at those right now. It's interesting stuff, but it's kind of not relevant to what I'm talking about today. Okay, so these are the different types of switches we can experience, right? So we have our original stimulus. So this thing in the middle is kind of meant to describe the different orientations that are drawn from the stimulus, right? So there's a mean orientation, but there's some variability around that. And then there's our blue option and our orange option. Okay, so this is where we started out. So we have our stimulus that's kind of dynamically changing. The stimulus mean orientation never changes. I should note that as well. It's just being randomly drawn on each new frame. And there's different ways that the stimulus can switch, right? One of them is to sort of maintain the exact same level of difficulty. And that is by actually just flipping the blue response alternative and the orange response alternative, right? So the orange one's leaning left here, and we just flip it. So the blue one's leaning left here, the orange one is leaning right. If we just do that, we don't see any change in accuracy, right? So people are actually just as accurate when the stimuli flip sides as when the stimuli don't flip sides. But they're a little bit slower in this condition, right? And some of this might be because they've been told that this is going to be a switch trial, right? So these trials are separate from these trials. They know if a stimulus isn't going to change, that it's not going to change. And if it's going to flip, then they know something about the stimulus is going to change. And so response times are actually quite a bit slower in this condition. And so you can kind of think of this as sort of a second control, right? So this is a control where the stimulus doesn't actually get any harder. They just have to remap the motor response from one response to the other response. Okay, so in addition to that, the stimulus can either, the overall decision can actually get easier, or the overall decision can get harder. There's a couple ways where it can get easier. One is that, well, our target, right, our blue response alternative at the start was actually a little bit closer to the stimulus. So we're just going to call that the target. One is that the blue stimulus can actually get even closer to the orientation of the stimulus, right? So that makes things a little bit easier. And people get faster and more accurate when that change happens in the stimulus, compared to a condition where there is no change in the stimulus. Similarly, we can actually rotate both the response options. So the blue option can move and the yellow option can move. Or we can move the distractor options. We can move the yellow option further away, so it's clear that the stimulus matches more closely to the blue stimulus, right? So those are three ways in which we can kind of make the decision easier by actually changing the locations of response alternatives during the course of the trial. We can also make it harder, and basically the ways to make it harder are the opposite of the ways to make it easier, right? We can either make the distractor more similar to the stimulus. We can rotate them so the distractor gets more similar and the target gets less similar. Or we can move the target response alternative and make it harder by moving that further away from the orientation of the stimulus. It should come as no surprise that all of those manipulations both slow down people's response times and result in lower accuracy. But the key here, and the thing that we're really interested in, is actually the manipulations that make the decision easier, right? So if somebody is just maintaining support for each response option separately, then making a decision easier by switching the response alternatives shouldn't actually help anything, right? Because they have to throw out the information that they already have, and they have to start new because they have a new response alternative, and they don't have any information for that response alternative yet. And so the fact that we're actually getting faster response times and higher accuracy in the conditions where the response alternatives change indicate that what people are actually storing is information about the stimulus, and then they're mapping that onto response alternatives as they show up on the screen. Right? So the fact that they can flexibly adjust in these conditions is really particularly important. And so I talked before about pre-accumulation sorting and post-accumulation sorting, whether or not they can handle this kind of effect, right? So the fact that people speed up when the response alternatives change and they get more accurate at the same time, right? That fact indicates that we have to have some information about the stimulus that isn't just described in terms of support for a particular response, right? And so as a result, circular diffusion model, geometric model, and this first instantiation of the spatially continuous diffusion model, they can all handle these shifts in response. But this pre-accumulation sorting model, right, this kind of accumulator model can't handle it because it has to throw out all the information it had for a particular response, right? So if the yellow option disappears, then you'd have to throw out all that evidence and start over. You wouldn't be able to speed up and have higher accuracy. Okay, so what do we get out of this? The main message is that, well, evidence representations and decision-making are not alternative specific, right? So if we just have an accumulator model where we have support for A, B, and C, that kind of model, if that's the only information we have about the stimulus, is not plausible, right? So we actually seem to have some accumulated store of evidence that can be remapped when available options change. It seems to indicate that evidence is kind of sorted for different responses after it's already accumulated. And so our accumulator and our traditional diffusion models of binary and multiple choice are incomplete, right? So they're missing something. They're missing the stimulus representation. But again, they're not useless, right? There's all the past work that's been done on these things is all fine because those usually response options aren't changing. And in many cases, actually, the spatial continuous diffusion model and the normalized version of the geometric model reduced to diffusion models in a lot of cases. So there's nothing really wrong with using these models when your response options don't change. But ultimately, what we need is further work to kind of disentangle the representations of stimulus information from our representations of support for response options. And that's kind of the key thing that this seems to have highlighted here. Thanks for at least sort of online attending the talk. Feel free to email me if you guys have any questions or if you want any additional slides or anything.